Hey everyone, and welcome to the third video of the Combinatorics topic. This is on the pigeonhole principle, which is the second formal counting principle that we introduce as part of this topic and as part of the Year 11 specialist course on counting techniques or combinatorics. This is a principle that makes sense a lot intuitively, and it seems like it'll be very, very easy, but you can see that it leads to some very counterintuitive results and can actually lead to some of the most difficult problems that you face in Year 11 spec. So yeah, essentially the unit outline is just solving problems and proving results using the pigeonhole principle. I'll be going over the basic case of the pigeonhole principle and the generalized case of the pigeonhole principle, and then I'll give you some examples of where both of those might pop up in a test question or exam question. If you have any questions related to this or my explanations weren't good enough, make sure you let me know in the comments and I'll upload some supplementary content or re-upload this video. Okay, so in this video for the pigeonhole principle, I'm first going to go over the basic case of the pigeonhole principle. And then second of all, I'm going to go through the generalized case. And for each of these scenarios, there are generally two ways of answering a pigeonhole principle question. The first one I'm going to call the worst case scenario approach. The worst case scenario approach. And the second one I'm going to call literally the pigeons and pigeonholes approach. Pigeonholes approach. Okay. So, to start off with the basic case, what the pigeonhole principle says is that if n plus 1 objects are placed into n holes, then at least one hole, or then some hole, contains at least two objects. Okay. Now, let's say I have, for example, two pigeonholes, and I have three pigeons, which I'm going to represent by these black circles, or maybe let's make them orange. These three pigeons. Now, if I want to go down the worst case scenario route, where I am trying to maximize the number of pigeons in one pigeonhole, the worst case scenario is that one occupies this one occupies this one, and then the third must occupy one of them. So the maximum number of pigeons I can get there is 2. That's the worst case scenario route. Alternatively, the way I can consider it is I can say I have 3 pigeons and I have 2 pigeonholes. 2 pigeonholes. Now, the number of pigeons I have in one pigeonhole in the worst case scenario will be given by the ceiling of the pigeons divided by the number of pigeonholes. In this case, that's equal to 1.5, but because I'm finding the ceiling, which is this, I think I already introduced you to the floor in the previous video where you round down. The ceiling involves rounding up. 3 divided by 2, in this case, is equal to 2. Because it's 1.5, rounding up, we get 2. And hence, we have at least 2 pigeons in some pigeonhole. Okay, so this is the pigeons and pigeonhole approach, which I discussed in that previous slide. And then the other way was the worst case scenario approach as an explanation. So if we take one example, let's say I have 13 red socks, I have 10 blue socks, and I have 8 green socks. Make that capital, 8 green socks. And I want to figure out how many socks do I need to select at random to ensure that I have a matching pair. Okay, so in this case, because we don't clearly have pigeonholes, the pigeonholes in this case are the colors, right? And what I'm trying to find is the number of pigeons I need in order to have at least one pigeonhole containing at least 2 objects, right? So what I'm trying to find is the number of pigeons. When I'm trying to find the number of pigeons, the worst case scenario approach is the better approach. So in the worst case scenario, this is how I would answer this question. In the worst case scenario, after 3 selections, we would have selected 1 red, 1 blue, and 1 green. In selecting 1 more sock, we would inevitably result in a matching pair. Hence, we need to select 4 socks or 4 pigeons. Okay, so this is the worst case scenario approach. All right. And this would be approximately a 2-mark question. This is a relatively basic pigeonhole principle question. Okay. Now, let's say we deal with a more generalized pigeonhole principle. So we dealt with the basic case, but in the more complex case, we can deal with cases where we can figure out that a sum hole can contain more than 1 pigeon given a certain number of pigeons that we choose. So if at least mn plus 1 objects are placed in n holes, then sum hole contains at least m plus 1 objects. Let's say, as aforementioned, we have our 2 pigeonholes, and then our m, so our n in this case is equal to 2, and let's say our m in this case is equal to 2 as well. So in this case, we would have 2 times 2 is 4 plus 1 is 5 pigeons. Okay, so at least 1 hole will contain m plus 1 objects. If we consider the worst case scenario, we have 1 pigeon here, 1 pigeon here, 1 pigeon here, 1 pigeon here. Okay, so we have 2. And then in this case, we would have 1 more in one of those pigeonholes, leading to 3 pigeons in 1 pigeonhole, which is equal to m plus 1, since m is equal to 2. Okay? All right. So let's take a look at a case where we would deal with the generalized pigeonhole principle. Let's say we have 16 natural numbers that are written on a board. If you're wondering what a natural number is, it is an integer. It is any positive integer. Sometimes it does include 0, but in this case, let's say it doesn't, just for the sake of simplicity. It's any positive integer. Usually whole numbers are the ones that specifically, explicitly do not include 0. Natural numbers can include 0 as a positive integer. All right, so we have 16 natural numbers that are written on a board, and we want to figure out that 4 numbers leave the same remainder when divided by 5. Now, in this approach, it is easier to use the pigeons and pigeonholes approach. More specifically, we can figure out the number of pigeonholes by figuring out the number of remainders that we can have when we divide by 5. When we divide by 5, we can have a remainder of 0, we can have a remainder of 1, 2, 3, or 4. We can't have a remainder of 5, because if we have a remainder of 5, you can simply just divide that by 5 to get back to 0. Okay? So, 0, 1, 2, 3, and 4. All right, so in this case, we have 5 pigeonholes. Okay, so in this case, we have 16 pigeons because we have 60 natural numbers. We have 16 pigeons and 5 pigeonholes. Therefore, some hole will contain 16 over 5, and the ceiling of 16 over 5 equals 4 pigeons, according to the pigeonhole principle. Okay? And this is proved what we required to prove. So we have proved what we wanted to prove. Okay? And so this, again, would be approximately a 2-mark pigeonhole principle question. I hope that answers some of the problems associated with the pigeonhole principle. There are certainly more complex ones that you can get. And if you have a question, make sure you leave that in the comment section, and I can upload a supplementary content video where I tackle more complex pigeonhole principle questions, because these can get relatively difficult. Until then, I'll see you in the next one, which is combinations. Bye-bye.